Just a couple of quick examples of using rotational inertia. We're going to consider motions that the Earth undergoes for both of these examples. The first one we want to consider is Earth spinning once per day on its axis of rotation. You look up in table 8.1 of your textbook, and the rotational inertia of a uniform density sphere, radius r and mass m, is going to be given by 2/5 m r squared. The Earth is not exactly uniform in density. The density does vary, but that's a good enough approximation for this class. And so we put in values for the Earth, mass of 5.97 times 10 to the 24th kilograms, and Earth's radius 6.37 times 10 to the 6th meters will give us a rotational inertia for Earth's rotational movement. So going about an axis through the Earth itself, 9.69 times 10 to the 37, and the units are going to be kilogram meter squared. We don't have a shorthand unit for that in MKS, but rotational inertia will be in kilogram meter squared. Now if we consider not Earth spinning once on its axis per day, but the Earth's orbital motion about the Sun, so that revolution, if this were to scale, there would be about 100 suns would fit between the Sun and the Earth, so even this is not to scale. Earth is way smaller than that if that's the size of the Sun. In that computation, the Earth is essentially just one point mass. So if you look at our sum over different parts to add up the rotational inertia, in this case it's just going to be one term in the sum. So I have the mass of the Earth times the distance between the Earth and the Sun, semi-major axis of our orbit, a squared. So again, we'll have the mass of the Sun and then our distance away from the Sun, 1.50 times 10 to the 11th meters quantity squared, which will give us a rotational inertia vastly bigger. Even though the mass of the Earth is the same, the distance to the point we're rotating about is very different. So 1.34 times 10 to the 47th kilogram meter squared.